Where's the remote? Oh, yeah. Okay, so we're looking at question 3, yeah? Um, so you have a n by n table, and you write a number in each cell, and the cell is called good if it shares a side with another cell that's 1 greater and another cell that's 3 greater, yeah? So it has to be 2 different cells. Alright. What is the greatest possible number of good cells? Yeah. See, it's kind of funny, like if you have this kind of question is easier, I think, and I can actually prove this to you in some experimental way that this kind of question is easier if you have less things to think about. Okay? But that doesn't mean you've solved the problem completely, right? Like for example, it doesn't say that um the numbers have to be integers. It doesn't say the numbers have to be positive, okay? Um so but if you're not aware of those issues, it might actually have helped you because you've complicated it less and confused yourself less, right? Okay, so this is a good example of a problem where you could actually have more trouble with it the better you are. Yeah, there's levels to this. You know what I mean? So it's like you don't see the issues, you see the issues but can't solve the issues. You see the issues and you can solve the issues. Okay, so the kind of the worst place to be practically is the place of seeing the issues but can't solve the issues. Then you need to team up with someone that can solve the issues. Okay, so you all got the construction, I think, yeah? So the construction, I think once you realize that like you probably started with like the checkerboard thing at some point and you got half, right? But then like for the 3 by 3 you get like 5, and once you realize maybe 5 is not the most, you can get 6. You got the full answer from there. Yeah? So basically from 3 by 3 you realize the answer is not 5. Yeah?
Uh-oh.
But you think the answer is 5?
I couldn't find better construction.
Wait, that was the problem.
That was probably actually the problem.
Okay.
Oh my god, that's why.
Okay, so 1. So you can actually log that like the smallest number is 1. Yeah. You can add to every cell and it doesn't change the conditions. Yeah. So you can actually make this one good by just doing whatever is needed, right, in these cells. Okay. And the interesting thing is you can actually make both of these cells good at the same time. Okay. So you might not have been able to do that because the middle one might conflict, right? But it's kind of nice that you can make that a 5 and it works. Yeah. So you just do the same thing on the other side and you get 6.
I started in the middle. That's probably why.
Hmm.
Because
Yeah.
starting in the middle, like there's more options.
Okay. So that tells you, so in general, you can kind of just start from the corner and work your way towards the middle diagonal, right? And then you just reflect it to the other side. So that'll give you n squared minus n, you know? And it's actually pretty convincing.
Oh, I got it then.
Huh?
I solved it.
What?
I solved it then. But I actually got n squared minus n.
There's still more to this. No one accidentally solves it.
No, because
That's why it's a proof.
I was thinking of like, no, because for every like 2 squares, I joined up an edge between them. And then we'll have a certain number of edges. It's actually, I think it's 2n squared minus n edges. But then for each square to be a good square, it needs to use up 2 of the edges. So that gives us n squared minus n.
Oh, so you got the other direction first. Oh, that's good. I thought that was the harder direction. I thought so
What?
because you have more possibilities to look at.
Yeah, wait, so that shows that the maximum is n squared minus n.
Yeah.
So then I just have to like come with a case to like show that it works right.
That's what we just did. Yeah.
Yeah, and it's all done.
Yeah. Okay, so
So it's done.
Okay, so this is like, and it's a pretty large number of cells, right? You're only missing the main diagonal, basically. So, like, if you were to go with something, this is probably something very convincing to go with. Half of them is not as convincing because there's still a lot more you could do, right? Here, it's basically all of it already. I think if you just do like a proof, there's a nice case bashing kind of proof you can just do for like 3 by 3 and 4 by 4. If you should at least be able to do that to prove that in by 3 by 3 and 4 by 4, it's actually the right answer. You know? And then you can have more confidence embarking on trying to explain why that's the actual answer. You know? I think, I mean, if you go with the half of n squared thing, it works on 2 by 2, but you know it doesn't work on 3 by 3, so that can't be the answer,
I
right?
did it like 2 hours ago.
Okay, so now why can't it be more, right? So this is the thing you had already.
Yeah.
Okay, so why can't it be more? Well, so one argument, I guess is this the same as your argument? So you count the number of um, borders,
Okay.
edge borders between the cells. Yeah. Um, and if you count them, you basically get n times n minus one for the horizontal ones, and n times n minus one for the vertical ones. Yeah. So you get 2 times n times n minus one borders. Yeah.
Yeah.
Okay. And you need two of the borders to be sort of the right relations, +1 and +3, to create a good cell, right? So you can at most make half of you can make at most one good cell for every two borders. So the total number of good cells you can make is at most half of this total. Yeah, yeah. So this is a pretty simple, but it's not as easy as it looks. Okay. So this is one of those things where like this is also like um if you think about it just kind of mathematically, you might not get to this very quickly. Okay. But if you think about it like in terms of Math Olympiad and maybe psychologically, you're like, oh, the answer has to be nice. Okay. So if you think about that too much, that'll ruin you, okay? Because you're just taking a shortcut. But one way I can sort of prove to you that this answer is kind of easier, the more you look for easy answers, is that I showed this to the junior class, so it's like the year 7 and 8 students, and they got this like almost instantly. Okay.
Got which one?
That it was at most n squared minus n.
Actually, that's what. Just
Okay. So the idea is right. So looking at the way that the cells transfer um, is um, is pretty natural anyway. But kind of just counting the borders is actually very simple. Um, can someone tell me something interesting about this? So not the construction, but the bound. Yeah. So counting the borders. Yeah. Can you tell me something interesting about that um, solution? Or maybe a reason why it might be difficult to come up with, or something interesting about it. Other than that, it's just like true. What might make it a little bit unusual?
no, I personally feel it was like
Very
normal.
usual.
Yeah, very normal because like you're dealing with relationships between adjacent groups. So you should like I always considered like not really the border, but I just join them up to the line.
Mm.
Like that's just what usually me because like this is one maps challenge question that I solved like induction and like I joined up the lines between like cells.
Okay. Jason, do you agree with Gabriel? That's just normal, or do you see something a little bit unusual about it? an issue?
I'm not sure.
Okay, so it's a little bit subjective, but do you think it's a little bit unusual that it doesn't actually use the 1 and the 3 at all? It doesn't use the condition, it just uses the bordering. The fact that it only uses the 1 and 3 are different. Well, does it use 1 and 3 are different?
Doesn't matter because 1 and 5 still works.
Does 1 and 1 work?
Yeah.
Okay, so if that's not used in the proof, then where is 1 and 3 used in the proof?
In the construction.
Yeah, it's using the construction because it's kind of very used to make that fit, right?
Yeah, I mean, if you took like 1 and 5, it still work. Because you had 1 and then 2 and then 6, and then the difference is 4. So you'd always add like a 5 to the right of the to the bottom of the right one.
Yeah. Yeah. So one another approach I had was kind of trying to sum up the numbers. Like if you sum up all the good cells, you kind of get something interesting, but it's nowhere near as. Actually, I have a little conundrum for you. Maybe I can put it up. So if you sum up, let's see, if you sum up all the good cells, right? If you call G the set of good cells, and like, the number, I'm gonna abuse notation and write the cell at the same as the number that goes in the cell. Yeah. So if I summed up all the numbers in the good cells, right? Yeah, so maybe this is just like a side question. Yeah. So if I summed up the numbers in the good cells, okay, and I summed up all the numbers that are in the not good cells, yeah. Hmm. The N's not the best letter. Where is beta? That's the total sum, yeah.
Yeah.
If I instead of taking the sum of the good cells, I take like the good cell and I sum the sort of the the cells that make it good, yeah. So if you have a good cell, the cells that makes it good has to be G plus 1 and G plus 3, right? Okay. So let me take an average and make it like um, G plus 2, yeah? So if I just sum G plus 2, yeah, across all the good cells, so is it true that this sum, I'm still summing up values which are less than the total sum? Yes. So this sum is less than the total sum, yeah? Okay. But this is equal to the sum of the G plus 2 times the size of G, yeah? Because the 2 gets counted for every G, yeah? Okay. So if this is true, we can kind of cancel the G sums, yeah? And we get 2 times the size of G is less than or equal to the sum of the things that are not in G. That makes sense?
Yeah.
Okay. So now there's some of the things which are not in G, I guess, like, so my question to you is, so this bound definitely does something, right? So it might not give you the n squared minus n, okay? But it definitely says something because if you have no non-good cells, then that just means you have no good cells, right? So you have to have some non-good cells to have good cells. That makes sense? Um, okay, so my questions are like, for example, okay, maybe just like an immediate question and like a long-term question. Okay, so immediate question, um, is this a bit weird because it seems like so we said you can translate all the numbers, right? If we add the same number to all the numbers, the problem should still be true, right? Okay. But here that's a bit weird because what if we subtracted, we made all the numbers like negative or something, right?
Yeah.
Then we seem to have no good cells ever. You know? There's something weird about that, right? So that's one thing. The second thing is, um, okay, maybe three things. The second thing is, I guess it's nice to note that the equality case of this happens, for example, here. Like if you add, let's see, 3, 5, and 7, you know, you get, wait, what, you don't get that here. Oh, that's kind of weird. You have 2, 4, 6. Yeah, so if you have 3, 5, and 7, okay, you don't get anything, you know, because 3, 5, and 7 add up to 15, right? And then you get the number of good cells is less than or equal to 7.5, yeah? But for some reason, if you let this be 0, 1, 3, right? This will be 2, 4, 6, okay? Okay. But 2, 4, 6 now add up to 12, okay? And then you get the number of good cells less than or equal to 6. Oh, that's crazy. Yeah, that's pretty weird. And so then back to the point 1, it's like if you decrease it again, would you get what, like 1, 3, 5? And then, or, and then you're saying the number of good cells less than 4.5, right? So something's wrong there, yes? Okay, yeah. And then, can you also see that this only seems to depend on, so we're saying the cells which are not good, right? Okay. But there's cells which are not good that don't make any other people good. And then there's cells that are like not good but make other people good. Like the role players. No, I'm just kidding. Okay, so
What?
so like they so I think so this is another question. Is it true that if you have a cell that's not good and it's not doing anything to make any other cells good, right? You can just set it to 0 and it won't affect the sum. See, if you want to get wishful thinking, you can get very wishful, right? But there's lots of stuff that's happening. Okay. And then the final thing is basically the conclusion of this. Does this actually work? Is something wrong here or not? Okay. And if so, if you can fix it, can you actually use this to solve the problem? Okay, does that make sense? I guess this is more tempting just because it takes into account the actual values of the cells.
Yeah.
But then the actual values of the cells is what's giving you the issues with all the proof as well. Okay? So that's like a side question if you're interested.
Side quest.
Yeah, side quest. Alright, you guys have any questions? Yeah.
Oh, this is so stupid.
Hmm.
And this is something. It's like two something voices. The question was only easy off of it.